This is kind of where we left off yesterday. I had you write down the table of anti-differentiation rules. Did you write these down?
Yes.
Okay. A couple of things that we want to make note of is it says there are no rules for the antiderivative of products or quotients. Again, when you see that, if you come across a product or a quotient and you're supposed to integrate that, you hope that you have a really nice calculator near you. Okay. This is just not something that we handle by hand. The other thing says the process of calculating an antiderivative is called antidifferentiation. Okay, I think we called it like underiving or something like that. I don't know. But just know that we're doing differentiation and we're doing it backwards. I wanted to look at a couple of these with you. This first one, it says a constant times a function. Its antiderivative is going to be a constant times the antiderivative. Okay, so if I had to find the antiderivative for some function f of x equals 6x squared, then its antiderivative f of x is going to be 6 times the antiderivative of x squared, which would be x cubed over 3. So the 6 stays. Okay, that's what you've got to see with the constant. You just keep the constant and then you take the antiderivative of whatever your variable term was. Also, if I have functions f and g and they're being added, then I add their antiderivatives. Okay, so that kind of leads us into the power rule, how it deals with like a string of polynomials. And you guys have seen that anytime we were taking an antiderivative of some function. So let there be, I don't know, a velocity function, v of t is equal to x cubed, or maybe t cubed, v of x. Let's let that be v of x. That's easier to fix. X cubed plus 4x squared plus x. Can y'all see this? And if I wanted to find its antiderivative, then I would anti-differentiate each of the terms, but I continue adding them just like they were in the original function. So what that's saying is like if it's f of x plus g of x, you could consider each of these terms to be their own individual little function. And so its antiderivative is still the summation of all of those terms after having been anti-differentiated. Okay? Yeah. Okay. The next one is the reverse power rule. Basically, I'm going to add 1 to my power, and then I'm going to divide by the whole new exponent. That's as long as n does not equal -1. And we looked at what happens when n is -1. Right. It looks like I ended up dividing by 0. The better option there is to take it to this 1 over x. Let f of x be 1 over x. And then its antiderivative is the natural log of x. What's the antiderivative of e to the x? E to the x. Okay. The antiderivative of b to the x is going to be b to the x divided by natural log b. So I want you to think about that. Because if I'm going to take the derivative of b to the x, what's the derivative of b to the x? B to the x natural log b. Well, if I say that the derivative of b to the x is just b to the x, and I don't divide by that natural log of b, then I gain a natural log b. Does that make sense? Kind of?
Let's say it does.
Let's just memorize it. Okay, fine. Then it gets a little tricky here. One that you see really commonly is secant squared x. You've got to know that the antiderivative of that is tangent x. That's one that's going to show up a lot. Okay. We get into inverse functions, and there are only 2. What's the difference in 1 over 1 minus 1 over the square root of 1 minus x squared? You should remember that sinus is minus. So if I see this guy, I know that its antiderivative would be sine inverse. But what if it was 1 over negative square root 1 minus x squared? What's its antiderivative? Cosine inverse. That was on our table that we had to memorize in the first place. So 1 over negative square root 1 minus x squared. That antiderivative is going to be cosine inverse of x. And then 1 over 1 plus x squared. That's going to be tangent inverse of x. Cool? Any questions on that? Okay. I feel like I should give a disclaimer to Arlette, who may be watching this later. There's a big old fly in this classroom, and if we finally get it, we're going to celebrate. And it's going to be loud, and you're not going to know what's happening. Okay. I need to get on that page here. I didn't even open my book yet. I just started talking. We almost get it?
Almost.
I'm telling you, it's the whole thing. Like, Nikki, what are you doing back there if you're not trying to get this fly?
It's down below you. Above you.
Wake up, Sawyer.
Yeah, Sawyer.
Sawyer, you have to play.
Kill the fly.
When it flies in front of
There's a huge fly.
No. He actually got it. No.
Where'd
Get
it
the
go?
textbook.
It's gone.
Y'all know that when President Obama was president, they were in an interview. Do you know about this?
Yeah,
And he caught the fly?
Yeah.
I need Nikki to have that kind of skill set. Johari does. I promise you Johari has the skill set. Give it, Johari, take care of this. Oh, do not let go. Let's not let go. Why? Okay, note to Arlette, we got the fly. Here we are. We're like 15 minutes later, and we're going to do some calculus. All right, so this is going to be example 2. And it says, use the table of anti-differentiation in order to kind of handle this particular problem. Okay. So it says, find all functions of g such that g prime is this business. So we're looking at the derivative, and we're trying to go backwards to g. Can y'all see that that's what's happening? What I want you to do right now is write down that g prime equation. Write it, yeah, it looks like a quotient rule. It looks like, I can't do this, because we don't have any rules for differentiating a product or differentiating a quotient. But what we're going to do with this g prime equation is we're going to simplify it. And we're going to put it in a form that we can use anti-differentiation rules. Okay, so write it down first in this form. And then right below it, we'll start simplifying. Are you satisfied? Yeah. Okay. Okay, so the first term here is 4 sine x. I can handle that one. That's a constant times a function. I can handle that differentiation or anti-differentiation, so I'm going to leave it. That term's good with me. But we're going to move on to the next piece. And what we have here is a binomial divided by a monomial. Okay? Let it be like a plus b divided by c.
We can pull c from both of those terms.
Correct. So anytime this is the setup, you can multiply a, or you can divide a by c, and you can also divide b by c. So the rewrite on this particular mumble jumble is to take that 2x to the 5th divided by x minus square root x over x. Okay, so each piece of the top can be split, and you can divide both by the bottom, which lets us simplify even further. So the 4 sine x is still 4 sine x. But the 2x to the 5th divided by x can now be written as what? 2x to the 4th. You see how that's nice? Okay. And then let's consider this second one as it would be with exponents. Let's let it be x to the 1/2 over x. If I'm dividing like bases, what do I do? What's the rule?
Subtract the exponents.
Subtract the powers. So half minus a whole
Is a negative half.
is a negative half. So minus x to the negative 1/2. Now we can use anti-differentiation. Okay. So term by term here, g of x is going to be, let's do the antiderivative of 4 sine x.
Negative 4 cosine x.
Okay. So it's going to be 4 times the antiderivative of sine x, which would be negative cosine x. Are y'all with me on that? If you're not sure, look at your table. Brooks, hold on to that, Brooks. We're gonna need that in just a minute when we get to the end. You're on. Okay, plus 2 times the antiderivative of x to the 4th, which is going to be
2x to the 5th over 5.
x to the 5th over 5. Everybody seeing how we got that number? Okay. Minus, and then we have x to the negative 1/2. The rule is add 1,
So x to the half.
so x to the 1/2, and then divide by the new power, which would be half. So,
Divided by 2. Right?
yeah, really rudimentary, it would be x to the 1/2 over 1/2. Let's clean that up in our next step. But we're not going to forget what at the end?
Plus C.
Plus c. Brooks, there's a reason you're here, big guy.
You get to say plus C.
You get to say plus c. All right, so g of x, I like the first term. Negative 4 cosine x. That one's fine with me. The second one I would call 2/5 x to the 5th. Yeah? What is it to divide by half?
Multiply by 2.
To multiply by 2. So the next one's going to be minus 2. We could call it x to the 1/2. We could call it square root x plus c. There is our general antiderivative. What made me know that I needed a general antiderivative is the fact that it says find all functions of g. Find all functions of g such that. Not find g when, but find them all. So the plus c, the arbitrary constant, handles that this could be anywhere on the plane. We looked at that kind of picture yesterday. Okay. Capiche? Yay. Let's go on. Now I'm looking for... got a whole bunch of pictures here. This one. All right, example 3. It says solve a differential equation. Find f. If f prime of x equals e to the x plus 20 over 1 plus x squared, and f of 0 equals negative 2. That's what we call, this right here is what we call an initial condition. Initial condition. What is it when x is 0?
Negative 2.
Is your y? No, I know that that's what this is. But on a function, when x is 0, where are we located? On the y-axis. On the y-axis. Sometimes at the origin, if x is 0 and y is 0. But usually speaking, when they tell me f of 0, they're giving me a y-intercept, also known as an initial value, also known as the constant. That's your constant. Your y-intercept is the constant. So they're telling you what c is. They're telling you when x is 0, think about it, term by term, I'm going to zero out everything that has x in it. So what's going to be left? The constant. Okay. So a lot of times when they're telling me this initial condition, they're giving me the value that they want me to use for c. Okay. All right, so let's go. F prime is this. So term by term, the antiderivative of e to the x is e to the x. What if I looked at this term, this big quotient that I'm about to be real confused by, as 20 times 1 over 1 plus x squared?
That is a thingy.
That is a
That's
thingy.
tangent inverse.
It's tangent inverse. So plus 20 times, what's the antiderivative of that? See, I pulled that 20, now it's acting like a constant, right? So the antiderivative is just going to have 20 times the antiderivative of 1 plus x squared, which that is a thingy.
That's tangent inverse.
That's tangent inverse. So 20 tangent inverse of x. And then plus c. This is the general antiderivative.
We have a C.
But we have an initial value. But watch. They say f of 0 equals negative 2. How do I know that's c? It's because when, pause. It might not be c. It's what happens when x is 0.
Oh.
No.
So f of 0, what is f of 0? F of 0 is negative 2. So I'm going to have to set this business equal to negative 2, and I will solve for c. Okay, it's not always guaranteed to be your c. Here I am, playing the advocate over here. It's not always c. Okay, I walked you right into that one. You're going to have to plug in 0 and set it equal to what number they say is f of 0, and then solve for c. What's e to the 0 power? 1. What's 20 times, what is the tangent inverse of 0? Think of your tangent graph. 0.
0. Yeah.
0. So 20 times 0. What's tangent inverse of 1?
I'm scared to answer.
Tangent inverse of 1? These are the most common. You have to know these two things. Tangent inverse of 0 is 0. Tangent inverse of 1 is... So tangent is the ratio sine over cosine.
Yeah, inverse is the other way around.
So inverse is the other way around. So when does sine over cosine equal 1? When are they the exact same number? So that when I divide them, I get 1. When does that happen? 45 degrees, which is pi over 4. So 2 fun facts for tangent inverse. 1, tangent inverse of 0 is 0. 2, tangent inverse of 1 is pi over 4. You're going to see that guy. You're going to have to know it. Okay? Okay. So that zeroes out this 20 business, but we still have a plus c on the end. Negative 2 equals 1 plus 0 plus c. So c must be negative 3. So in my general antiderivative, instead of putting plus c, I'm going to put minus 3. There's my answer. I'm going to solve for c using that initial condition. Y'all understand why it's not always just given to be? Now, if this thing was polynomial and I did zero out every single term, what I would be left with would be the y-intercept c constant. Life is good. But it's because they're special, and I didn't just get to zero out every term. I had to evaluate every term at 0. Cool beans? Okay. I don't think I got a picture of this one. This is going to be example 4. find f if f double prime of x is 12x squared plus 6x minus 4. And they give us two conditions. F of 0 equals 4 and f of 1 equals 1. Okay, so give me a physics thing. What are we doing here?
Finding position from acceleration.
We're finding position from acceleration. If they give me the second derivative, that's equivalent to, if in particle motion, this is acceleration, right? And they're asking me for f. So they've given me an acceleration function, and they're asking me to find what's the position function. Can y'all see that that's what's happening here? So what do we have to do? We have to anti-differentiate 2 times. So the first time we anti-differentiate, we'll be coming up with f prime. Okay. So we're going to keep the constant. We're going to anti-differentiate x squared, which is to call it what? X cubed over 3 plus 6 times x squared over 2 minus 4 times x. If there wasn't an x, it's a constant. That means I've got to give an x to it. X to the first power over 1, just x, plus c. Okay. At this point, guys, I don't plug in the 0 and solve for a c, because this is f of 0. If it had said f prime of 0, then I could put that 0 in here. But this is f of 0, and what I have right here is f prime. Okay. Let's clean this f prime up before we find its antiderivative. What's that 12 over 3 going to come out as?
4x.
Okay, so 4x cubed plus 3x squared minus 4x plus c. I'm good with it. Are y'all? Simplify it. Now let's take its derivative. Are you with me?
Yeah.
I mean, not its. Find its antiderivative. This is where I get tangly, because now I've spent a whole semester deriving, and then we're going backwards, and it's very hard to go back and forth. All right, so we're going to keep the 4, and then this is going to be x to the 4th over 4 plus 3 x cubed over 3 minus 4 x squared over 2 plus cx. See, now he's a constant, and he gets an x when it rolls down into the next antiderivative.
How do we calculate that?
And then what? There's a constant at the end, plus d, a new constant.
Well, we know what that is. So it's a polynomial, so we know what that is.
Okay, so let's simplify this guy first. This is going to be our general antiderivative for f. It's going to be x to the 4th plus x cubed minus 2x squared plus cx plus d. Are you with me? Okay. You can only plug in one of these at a time, right? I can't put in 2 different values for x at once. So I would plug in the 0 first. When I do that, f of 0, everything here is going to 0 out except d. F of 0 equals d, so what does that mean? D must be 4. That's helpful, because now I can find f of 1, where I put in a 1 everywhere. Plus 4 on the end. And that is set equal to 1 also. So 1 is going to equal 1 to the 4th is 1, plus 1, I'm now at 2, minus 2, which is 0. 0 plus c plus 4. Do y'all agree with that? 0 plus c plus 4, so c plus 4. c is negative 3. Okay. So finally, f of x, I'm going to squeeze it in down here at the bottom, is going to be x to the 4th plus x cubed minus 2x squared minus 3x plus 4. There is our antiderivative position. Okay. Sophia, Yaya, are y'all okay? I'm trying to keep you guys in mind. Like you've never seen this before. Are we doing okay with that? Yeah. Everybody else good here? Do we need to walk back through any of that? No? 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 Seth, what's wrong?
I'm tired.
Are you not entertained? I feel like it's the guy on Russell Crowe, Gladiator.
I don't know.
Sketch. Oh, gross. Okay, here's example 5. Sketch an antiderivative. Sketch an antiderivative. So what we have here is a derivative. Can you see that? What we're supposed to do is draw the antiderivative based on this information.
General drawing or?
Okay, so general drawing, that's a great question. A general drawing or the drawing, okay? If it was general, our antiderivative that we sketch here could be located anywhere on the y-axis because the plus c lets it be anywhere, right? But they say start at f of 0 equals 2. So begin your drawing at the y-intercept, okay? What I would do is I would get as close to this guy on paper as you can. Draw this one on your paper so that then you can kind of follow along and draw the antiderivative while you're at it. Draw this picture on your paper. This is f. This is the derivative. They want us to go backwards and draw the antiderivative. Okay? It would be pretty easy to draw the derivative of this one. The hard part's going to be going in reverse. And the antiderivative is going to begin at 2. 0, 2. So this is going to be your starting point right here. And when you're ready, we'll talk through it. Okay. So I'm going to kind of break the derivative up for you into intervals. On the first interval, let's go from 0 to 1. This is the derivative. What do you know about the derivative on this interval?
It determines the slope of the other one.
Okay. And what are you're looking at the derivative. What do you know about it on this interval? Where is it located?
Below the x-axis.
It's below the x-axis. So that indicates if this is the derivative and the derivative is below the x-axis, then the derivative is negative. So what does that tell you about your function?
It's going to go down.
Your function's decreasing. So on the interval from 0 to 1, your function should be decreasing. Okay, does that make sense? And so then on the interval from 1 to 3,
It should be increasing.
your function should be increasing. However, at 2, something happens. Okay? On the interval from 1 to 3, it should be increasing. Do y'all agree with that? Okay? But at 2, there's an inflection point. Okay? So while it's increasing, and it doesn't have to go, I drew mine all the way down to the x-axis. It doesn't necessarily have to do that. That might be confusing for you. But while it's increasing, it changes from being concave up to now being concave down. And the reason we know that happens is because the second derivative is 0 at x equals 2. Can you see that? At 3, so these x-intercepts on my derivative should mark what on my function? X-intercepts on the derivative should mark
Mins and maxes.
extrema on my function. So this is everything we did right before Christmas, backwards. If I'm looking at an x-intercept at 3, then I should know that that means my function itself had a maximum there. Notice that at 3, the derivative goes from positive to negative. So my extreme should be a maximum. My function should go from increasing to decreasing here. Are you with me? Does it ever come back up?
No,
Does it ever start increasing again?
no,
How do I know that?
because it asymptote.
Because from 3 to positive infinity, the derivative is below the x-axis. It's positive. Can you see that? So right here, after 3, it turns, and it never comes back up. Does it do anything special?
I mean, the slope is permanently like decreasing.
It's always decreasing.
It's like it's always getting less and less steep too, because the derivative's getting closer to 0.
Okay, I'm drawing mine like this. Can you tell that at 4, something happens on mine? Yeah, right here. There's an inflection point that I put in mine. It's still decreasing. It's decreasing forever. But why did I put that inflection point right there at 4? Yeah, because look at the derivative right down here. It seems like there's a horizontal tangent line, meaning the second derivative is is 0. So that happens at 2, and that happens at 4. So on my function, I see inflection points. I see changes in concavity at 2 and at 4. Can you see it? Oof. It's kind of twisty. Any questions on that? No? So we're going to wrap up 5.1 tomorrow. You'll have a tiny, tiny bit of class time to have a work day. I would be working on that homework in the background and trying to get it. We're already a whole day behind this week. Okay?
Start the homework.
You can start the homework, and I would be getting on top of that as much as you can.